Design a cylindrical can of volume 900 cubic centimeters so that it uses the least amount of metal. In other words, we need to minimize the surface area of the can because we're looking for the least amount of metal, in this case, including the top and the bottom. The volume of the cylindrical is V equals pi r squared h, and we're given that this volume is 900 cubic centimeters. This is the constraint that we will need to work with. We will use this constraint somehow to isolate one of the variables in the objective equation. The objective is to find the least or to minimize the surface area, where the surface area is the area around the can and the area on the top and the area at the bottom. Both the top and the bottom are simply pi r squared because we can assume that the top is a circle and the bottom is a circle. For the area of the lateral sides of the height h, the area is the height times the circumference of the circle at the bottom. We can think of the circumference at the bottom as the length of the rectangle. If we were to cut the can and straighten it out, the lateral side would form a rectangle with height h and the circumference 2 pi r. The area of this lateral side is the area of the rectangle 2 pi r times h. We now need to express the equation in terms of r or h only, but we see that the surface area is 2 pi rh plus 2 pi r squared. 1 pi r squared plus another pi r squared, top and bottom, is 2 pi r squared. So we will rewrite this equation in terms of r. We need to find h in terms of r, but that is where the constraints equation comes in. H is 900 over pi r squared. Replace h in terms of r. We have the surface area in terms of r as a function f is now 2 pi r times 900 over pi r squared plus 2 pi r squared. Simplifying this, we have pi canceled out. R divided by r squared is r in the denominator. 2 times 900 is 1800. We still have the second term, 2 pi r squared. We then find the derivative of this function to find any critical number. The derivative of 1/800 over r is negative 1800 over r squared. The derivative of 2 pi r squared is 4 pi r, and we set this equals to 0. Solving for r, we move the term negative 1800 over r squared to the right hand side to obtain 1800 over r squared positive. We then cross multiply to get 4 pi r cubed equals 1800. So r cubed equals 1800 over 4 pi. 1800 over 4 is 450, and then we still have pi in the denominator. R is the cube root of 450 over pi, or 450 over pi to the 1/3 power. This is approximately 5.23 centimeters, but we will use the actual number. R equals 450 over pi raised to the 1/3 power. We then need to calculate the height of this cylinder. The height in terms of r is 900 over pi r squared. This is 900 over pi times 450 over pi. 1/3 squared is 2/3. We then manipulate this expression to write 900 over pi over 450 over pi to the 2/3. The numerator is 2 of 450 over pi, and the denominator is 450 over pi 2/3. And so this is 2 times 450 over pi to the power 1/3. But we write it in this form to see that this is actually twice the radius. This is 2 times 450 over pi to the 1/3 is r. And so this is approximately 10.45 centimeters. To design a can with a volume of 900 cubic centimeters with the least amount of metal, we would need the height h to be twice the radius. In this case, the radius is approximately 5.23 centimeters and the height is approximately 10.45 or 46 centimeters. How do we know that this will give us the minimum value? If we check the sign of the first derivative at prime, the cut point is at 5.23. Starting from 0 to 5.23, if we pick any number and check the sign of f prime, we will see that f prime is a negative. Pick x equal 2, for example, or r equal to negative 1800 over 2 squares plus 4 pi times 2 will be negative. And if we pick any number after 5.23, 100 for example, we will see that f prime is positive. And in this case, the function is decreasing and then increasing. The function attains its minimum value at 5.23. And there's only one critical number here. This has to be the absolute minimum as well.